This is Io. Jupiter has been eating it alive for 4.5 billion years, without pause, without variation, without end. And in all that time, Io has not died, because Jupiter has never stopped. Io is the innermost of Jupiter's 4 large Galilean moons. In size, it is roughly comparable to Earth's moon, about 3,600 kilometers across, with a similar mass, sitting in the same category as a body we tend to think of as geologically cold and long dead. It orbits Jupiter at a distance of approximately 420,000 kilometers, completing a full circuit every 42.5 hours. From Earth-based telescopes, for most of human history, it appeared as little more than a point of light circling the largest planet in the solar system. That was the version of Io we thought we understood. Then we got closer. Io has more than 400 active volcanoes, not historically active, not dormant, not intermittent. Active right now, at this moment, erupting continuously across a surface roughly the size of Western Europe. Some of those volcanoes are launching plumes of sulfur and sulfur dioxide 500 kilometers above the surface. For context, the most powerful volcanic plumes ever recorded on Earth barely reached 40 kilometers. Io's plumes climb more than 12 times higher. Some volcanoes have produced lava lakes the size of small seas, and the surface they cover is so geologically violent that Io has not accumulated a single impact crater in its entire existence. Every crater it has ever received has been buried under fresh lava before it could survive. The largest lava lake on Io, a feature called Loki Patera, is 202 kilometers in diameter. That is roughly the distance from London to Nottingham, bent into a circle and filled with molten rock. The surface of this lake overturns in slow, advancing waves, exposing fresh magma beneath a cooling crust over and over, in a cycle that has been running for longer than our species has existed. Because of that continuous resurfacing, the terrain we see on Io today is no more than a few million years old. In 4.5 billion years of existence, Io has erased itself completely, again and again, hundreds of times over. This is not an exaggeration. This is not a metaphor. This is what Io does. But here is what is easy to forget when confronted with those numbers. From a distance, Io does not look like any of that. The Voyager 1 spacecraft, approaching Jupiter in March 1979, sent back images that prompted scientists to compare the moon's appearance to a pepperoni pizza. The colors, yellows and oranges and deep reds and brilliant whites, come from sulfur compounds deposited across the surface by centuries of volcanic activity. They are the residue of the violence, but they are also disarming. Seen against the black of space, Io looks almost cheerful, cartoonish even, warm. It is none of those things. Those yellow plains are coated in sulfur dioxide frost. The average surface temperature away from the volcanic hotspots is roughly -130 degrees Celsius, cold enough that the thin, unstable atmosphere partially collapses every time Io passes through Jupiter's shadow and the frost stops sublimating. It is a world of contradictions so total they should not coexist, simultaneously frozen and burning, dead-looking and more geologically alive than anywhere else in the solar system. A world that appears harmless at distance and becomes more violent the closer you get. We looked at it and saw a pizza. We were looking at something closer to hell than anything else the solar system has to offer. And the reason Io is what it is, the mechanism behind every eruption and every plume and every lava lake on its surface, has nothing to do with Io's own internal chemistry. It is not radioactive decay. It is not residual heat from formation. It is not plate tectonics. Io is volcanic for one reason and one reason only, and that reason is approximately 420,000 kilometers away and roughly 318 times more massive than the Earth. On the morning of March 9th, 1979, an optical navigation engineer named Linda Morabito sat down at her workstation at NASA's Jet Propulsion Laboratory in Pasadena, California, and did something routine. She was processing a Voyager 1 image of Io to check the positions of background stars, a navigational task with no particular scientific ambition. But when she enhanced the image to improve the visibility of those stars, something else appeared on Io's limb. A vast plume of material, arching hundreds of kilometers above the surface. Her first assumption was that it was another moon, partially hidden behind Io. That possibility was quickly ruled out. No known body occupied that position. What Morabito was looking at was a volcanic eruption, the first ever identified on a world other than Earth, rising from a dark volcanic depression on Io's surface that would later be named Peale. She later wrote that the sight moved her to tears. What made the discovery almost impossible to process was what had happened just days before. Stanton Peale, a physicist at the University of California, Santa Barbara, along with Patrick Casson and Ray Reynolds at NASA's Ames Research Center, had published a paper in the journal Science. The paper predicted, on the basis of orbital mechanics, that tidal friction from Jupiter's gravity would have melted a significant fraction of Io's interior, and speculated cautiously on the possibility of active volcanism. That paper appeared on March 2nd, 1979. Voyager 1 made its closest approach to Jupiter on March 5th. Morabito found her plume 4 days later. Theory and confirmation arrived within the same week. In the history of planetary science, it is difficult to name a more precise collision between prediction and reality. 8 additional plumes were identified in the Voyager 1 images once we knew what to look for. When Voyager 2 followed 4 months later, the surface had already changed. New deposits had appeared at features called Aten Patera and Surt, where there had been nothing before. Io was not simply volcanically active. It was volcanically active fast enough that 2 spacecraft passing through the same system months apart could document the repainting of a world. The question we have been working through ever since has one word for an answer: why? Io is roughly the same size as our moon. Our moon is geologically dead, its interior long cooled and solidified. Both bodies formed from broadly similar materials at broadly similar times. By every reasonable assumption we could make, Io should share the moon's fate: cold, inert, featureless. To understand why it does not, you have to understand what Jupiter's gravity is doing to it on every single orbit. Io does not travel around Jupiter in a perfect circle. Its orbit is elliptical, which means its distance from Jupiter continuously varies. When Io is closer, Jupiter's gravitational pull is stronger. When it is farther away, the pull relaxes. On the side of Io facing Jupiter, that pull is measurably more intense than on the far side. The difference in gravitational force across Io's diameter, what physicists call a tidal force, distorts the moon's shape. pulling it slightly out of round toward Jupiter. As Io moves through its elliptical orbit and that distance changes, the distortion shifts and flexes. The solid rock of Io's crust rises and falls by up to 100 meters with every orbit. Every 42.5 hours, the ground moves the height of a 30-story building. Then it falls back. Then it rises again. The tidal forces driving that flexing are approximately 20,000 times stronger than the tidal forces Earth experiences from the Moon. Bend a piece of metal quickly and repeatedly, and it heats up. The friction generated by that repeated deformation converts mechanical energy into heat. In a small piece of wire, the result is a faint warmth. In a moon the size of Io, flexed with that intensity every single orbit, the result is approximately 100 trillion watts of continuous heat generation. For comparison, Earth's entire internal heat output, the combined energy powering our tectonic plates, our volcanoes, every geothermal system on the planet, amounts to roughly 44 trillion watts. Io produces more than twice that, not from radioactive decay, not from any internal chemistry, from being squeezed. But here is the catch. Jupiter is not doing this alone. Io is held in that elliptical orbit, prevented from ever settling into a stable circle by two of its neighbors, and without them, none of this happens. Jupiter has 4 large moons. In order of their distance from the planet, they are Io, Europa, Ganymede, and Callisto. The 3 innermost of these are locked together in a gravitational arrangement called a Laplace resonance. For every 4 orbits, Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes exactly 1. This means that at regular predictable intervals, Io finds itself aligned with one or both of its neighbors. The gravitational nudges they deliver at those moments are small, but they are consistent, and they accumulate. They keep Io's orbit from ever circularizing. They prevent the tidal forces from ever easing. They make all of this permanent. Jupiter squeezes Io, and its neighbors ensure Io can never move far enough away for that squeezing to stop. The result is a surface that looks like nothing else in the solar system. Io's lava temperatures can reach approximately 1,600 degrees Celsius, a number that requires context to appreciate. The hottest lavas currently erupting on Earth rarely exceed 1,200 degrees Celsius. Io's lava is hotter by at least 400 degrees, more consistent with a category of extremely iron and magnesium-rich magma called ultramafic lava that Earth last produced in large quantities more than 2 billion years ago, before complex life existed. Some researchers believe certain Io eruptions push temperatures even beyond 1,600 degrees. The exact figures remain an area of active measurement. But even the conservative estimates place Io's volcanic output in a temperature category our planet has not visited since before the oceans had fish. Those temperatures drive the plumes. Sulfur and sulfur dioxide, superheated in chambers beneath the surface, are blasted skyward at speeds approaching 1 kilometer per second, roughly 3 times the speed of sound in Earth's atmosphere, climbing 500 kilometers before falling back as slow, silent showers of frost. That frost is what gives Io its colors: yellow, white, deep red. The residue of eruptions settling across the surface in layers we look at from a distance and mistake for something peaceful. And at the center of all of it sits Loki Patera. Loki Patera is a volcanic depression near Io's equator, 202 kilometers across, filled with an active lava lake whose surface area exceeds that of Lake Ontario. Its behavior is unlike anything we observe on Earth. The top layer of the lake cools and forms a crust, but that crust is denser than the lava beneath it, and periodically it sinks, exposing fresh magma that brightens in the infrared before slowly cooling once more. This overturn propagates across the lake in a wave, taking between 400 and 600 days to complete a full circuit. During Juno's close flybys in early 2024, scientists observed dark islands embedded in the lake's interior, rising from the molten surface like permanent features in a landscape that should not have permanent features, visible in images stretching back to the first time Voyager photographed them in 1979. Hot, cooling, overturning, again and again, without pause. And that is not the strangest part. For 45 years, the most contested question in Io science was not what its surface looked like, but what existed beneath it. The dominant theory held that Io harbored a global ocean of magma below its crust, a planet-wide reservoir of molten rock feeding all its volcanoes simultaneously. It was a reasonable model. Io's heat output demanded something immense. A global magma ocean satisfied that demand neatly. It was also wrong. In December 2023 and February 2024, NASA's Juno spacecraft made two extremely close flybys of Io, passing within approximately 1,500 kilometers of the surface. Scott Bolton, Juno's principal investigator at the Southwest Research Institute in San Antonio, framed the objective simply: measure Io's gravity at close range and determine once and for all whether a global magma ocean existed beneath the crust. The data came back unambiguous. Io's interior is mostly solid. There is no global reservoir of magma. Each of Io's 400-plus volcanoes is powered by its own individual chamber, a localized pocket of molten rock sitting directly beneath it. The findings were published in the journal Nature in December 2024, closing a mystery that had been open since the week Morabito found her plume. We thought we understood the plumbing. We had been wrong for 45 years. And then, 4 days before the end of 2024, Juno found something no one had anticipated. On December 27, 2024, Juno made another pass of Io, this time at a distance of approximately 74,000 kilometers, with its GIRAM infrared instrument trained on the southern hemisphere. Alessandro Mura, a Juno co-investigator at the National Institute for Astrophysics in Rome, described what the instrument recorded in precise terms: an event of extreme infrared radiance so intense it saturated the detector. The data, once reconstructed, revealed a volcanic hotspot spanning approximately 100,000 square kilometers, 5 times larger than Loki Patera. Its total power output exceeded 80 trillion watts, 6 times the combined energy output of every power plant on Earth, and the most energetic eruption ever recorded anywhere in the solar system beyond our own planet. The evidence suggested this was not a single hotspot, but several closely spaced eruptive centers firing simultaneously, driven by a vast interconnected system of magma chambers activating together. JunoCam images from subsequent flybys showed visible changes to the surface in the affected region. Something had shifted. What gets me is not the power output. It is that the instrument we specifically built to study the most volcanically extreme world in the solar system was overwhelmed by what it found. We have been observing Io for 46 years. It keeps finding new ways to exceed our models. If you could somehow stand on Io's surface away from the immediate danger of an active vent, the first thing you would notice is Jupiter. It would fill nearly 20 degrees of sky, a banded wall of orange and cream rising from the horizon, roughly 40 times wider than our moon, appears from Earth, close enough that its cloud patterns would be visible to the naked eye. The second thing you would notice is the cold. Away from the hot spots, the surface temperature sits around -130 degrees Celsius. The atmosphere is too thin to carry sound. The third thing, if you remained long enough to feel it, would be the ground. Slowly, almost imperceptibly, the rock beneath your feet would begin to rise. Not shaking, not cracking, rising. Over the course of a single Io day, that same 42.5 hours, the surface would lift you by nearly 100 meters before settling back and then beginning again. No noise, no warning, just the planet above you, pulling. There is a philosophical weight to all of this that is worth sitting with. Io is not geologically alive in the sense we usually mean. It has no internal engine of its own, no stored reserves of heat it is slowly spending. What keeps it alive is external, a gravitational force applied at a distance by a body that does not know Io exists. And what we have learned from studying Io is that this arrangement is not unusual. Europa, the next moon outward, is kept warm by the same resonance, more gently, and almost certainly harbors a global ocean of liquid water beneath its ice. Enceladus, orbiting Saturn, is similarly squeezed by similar forces and expresses a similar ocean through geysers erupting at its south pole. We are beginning to find exoplanets in tight orbits around large stars, where tidal heating may be the dominant geological process on the surface. Io was the first place we understood this mechanism clearly. It has been teaching us ever since what it means for a world to be kept alive against its own nature. Juno continues to pass Io on its extended mission, returning to the same region's orbit after orbit, comparing what it sees now with what it saw before. The volcanic event from December 2024 was still active in early 2025. Whether it continues now, whether it has carved new landscape or finally exhausted itself, is a question each new flyby is designed to answer. The surface changes with every pass. New deposits, new flows, features that exist in one image and not the next. Io does not accumulate a record of what it has been. It erases itself and starts again, as it has done continuously since the solar system was young. Jupiter has been doing this for 4.5 billion years. It will still be doing it long after every other sign of our civilization has gone quiet. Thanks for watching, and I'll see you in the next one.